This problem involves a beam supported by a pin and a roller. The beam has mass m and length L. The beam supports a box. The box size is A by A, and its mass is denoted by lowercase m. The box is attached to a counterweight through a cable that runs through a pulley. Our task is to determine the forces exerted on the beam by the supports. Alternatively, we can say that our task is to determine the reactions of the supports at the pin and the roller. We begin solving this problem by drawing a free body diagram that involves the counterweight, the cable, and the pulley. In drawing this free body diagram, first I recognize that the counterweight is attracted to the earth, or simply put, we have to put the weight of the counterweight on the diagram. Then I recognize that the pulley is originally constrained by a pin attaching it to the ground. The pin constrains two translations, and therefore, as I remove the pin, I have to compensate for that by putting a horizontal and a vertical force. Finally, I recognize that there is a constraint imposed by the remainder of the cable, and this constraint is a long extension of the cable, and therefore I put a force as shown. Next, I will consider the free body diagram for the beam, the box, and the cable. I will begin with showing the weights of the box, of the beam. Then I will show that the force exerted by the upper part of the cable on the lower part of the cable is exactly the same as the force the lower cable exerts on the upper cable. In other words, these two forces are equal in magnitude and opposite in direction. And to show that these two forces are dependent, I show the second force in green. Next, let me look at the left end, where the constraint is the pin. Since the pin constrains two translations, I put two forces on the free body diagram. On the right, I have a roller which constrains only vertical motion, and therefore I put a vertical force. These are two free body diagrams which are supposed to be sufficient for writing down equilibrium equations that will lead to the determination of the reaction forces. Let me begin with the first free body diagram, and I will write here the key equation, which is sum of the moments about the center of the pulley is equal to mg times r, where little r is the radius of the pulley, minus t times r. The reason these forces have the same arms is very simple. Both forces are tangential to the circle, and therefore the distance from the center is equal to the radius. Of course, this gives us immediately that the tension in the cable is equal to mg. Note that I could have written some of the forces on x and some of the forces on y. These two equations would have engaged the forces at C, Cx and Cy, and if it were necessary, I would be able to find those forces from those two equations. But I'm not going to do it here. I'm perfectly content with calculating the tension. Next, let me consider the free body diagram for the beam. I will write first the equation for sum of the forces on X, which is AX minus mg cos alpha equal to 0. Sum of the forces on Y involves the force AY mg sine alpha minus mg plus by. Finally, I need to write sum of the moments equations, and I will use the point A. In writing the equation, I will neglect the beam thickness. So let's begin. The forces AX and AY are not engaged because their arms are equal to 0. Now, the tension force, mg, produces two terms. The first term is due to a horizontal force, mg cos alpha, and the moment is positive, and the arm or the vertical distance is equal to a. The second contribution is due to the horizontal projection, which is mg sine alpha. The arm for the vertical projection is a horizontal distance from A to this location, and it's not that difficult to see that this distance is L minus A over 2. I recommend that you do a quick calculation showing that this is indeed the case. Next, I compute the moments due to the weights of the box, of the beam, and finally I compute the moment due to the reaction force By. Now I have three equations and three unknowns. To solve them, I will start with sum of the forces on X, which simply gives me the reaction AX equal to mg cos alpha. Next, I will proceed with the moment equation. The reason for that is that it involves only one unknown, By, and I can solve very quickly for this. And let me look at various terms involving this expression. The first term is simply the reaction to the mass. The second term is associated with the counterweight. So the counterweight reduces the reaction force. Finally, there is a contribution due to the fact that the box has its size, and this size produces moment. I want to pay your attention that if the size of the box is much smaller than the size of the beam, then these two terms disappear simply because A over L becomes small. Finally, I look at the equations for sum of the forces, and now I can substitute into this equation By, which has been already determined, to get AY. Again, please pay attention. The first term is due to the box and the beam itself. The second is due to the counterweight. And the last term is due to the fact that the box has finite size A, and this finite size induces certain moments. Thank you very much.